The title of this talk is Fair Outlier Detection. My name is Deepak and this is joint work with Savitha from IIT Madras. And I should mention here that this is the first work on fairness in automated outlier detection, and this falls within the broader umbrella of an emerging interest in responsible and ethical artificial intelligence across various tasks. So let's first look at what outliers are. So there was this book by Hawkins in 1980, which was titled Identification of Outliers. And this is pretty much the most quoted definition of outliers from outliers, which is from this book, which says that an outlier is an observation that deviates so much from other observations as to arouse suspicion that it was generated by a different mechanism. So in many cases, it is very easy to identify what an outlier is. So for example, here in this image, it's very clear as to which is the outlier and which feature characterizes it. It's not an outlier just because it's red, it's an outlier because of certain features. So we need to identify maybe in certain cases the relative importance of features that determine outliers as well. So let's look at outlier detection during the early times of AI and data-driven learning, maybe several decades back. So you could have used outlier detection to identify errors in data entry. So here I have an example where there is a person entering a lot of numbers, and it is quite apparent that the number 3 is an outlier, and it is potentially due to an error. He or she probably intended to enter another digit next to it and probably missed it. So you can use outlier detection to identify errors in data entry, and you can use outlier detection to identify faulty sensors if you're aggregating sensor data such as temperature in this case from across a wide variety of sensors which are in a geographically localized area, and you certainly have 300 degree Fahrenheit from one of the sensors. It's clearly a faulty sensor, and you might want to replace that sensor. So when you look at outlier detection now, things have changed. Now outlier detection is quite often used to identify suspicious activity, such as maybe a person putting something in a bag which looks suspicious, or other kinds of things such as an unusual benefit claim, so that it can be channelized in order to be scrutinized further than usual. So outlier detection is being used now to make decisions that affect people in very substantive ways. And it is often used also as an extra legal mechanism to shift the burden of proof. So if you are being flagged as an outlier, or if your behavior is flagged as suspicious, then typically the onus is on you, whether legally or whether by usual processes. Typically the onus is shifted over to you to prove your innocence. In the usual case, the onus is on the officer, is on the enforcement agency to prove your guilt. But here outlier detection kind of is used oftentimes as a way to shift the burden of proof. So why do we need to worry about fairness? There has been an increasing amount of work, especially in popular literature, such as these books. For example, the book Automating Inequality talks about how some of the big data algorithms are anti-poor, and there are works on how big data algorithms reinforce racism and various other kinds of biases. And this is just a snapshot. This is just a small sample of the various books out there which deal with this topic. So there is an increasing awareness of how big data algorithms need to be fair and need to be aligned with values in the society. So detecting suspicious activity, shifting burden of proof, and increasing scrutiny is among the most overt manifestations of big data decisions affecting humans. And whenever you're talking about making decisions that affect humans, then you would need to worry about fairness in any case. So let's look at fairness in outlier detection. So in the case of outlier detection, it's often used in order to identify abnormal or suspicious behavior, and it has wide applications in law enforcement, proactive policing, visa screening, insurance premium determination. So if you take a unusual route during your daily commute, maybe or if your speeds are or if your speed during a drive is judged to be unusual, then you probably would get a higher premium the next time that you're trying to renew your insurance. And offering medical tests based on wearables data, and so on and so forth. So when you want to identify what is abnormal, it automatically often entails a modeling of what is normal. And the model of normal is likely to be more influenced by the majority category since it is more prevalent. So when you use big data algorithms and anomaly detection algorithms, outlier detection algorithms, etc., it could lead to picking out minority demographic groups more frequently as outliers. And that is where you have the discrimination angle and the fairness angle to it. So when you think about fairness and outlier detection, you can think of it in different ways. One way, or the philosophy that we use in this paper, is to distribute the inconvenience of being classed as an outlier equitably across sensitive demographic groups. And this is inspired by this moral and ethical philosophy doctrine called luck egalitarianism, which says that distributive shares be not determined by factors of brute luck such as gender, ethnicity, etc. So one way to achieve this, if you have just one attribute on which you want to ensure fairness, which could be ethnicity, a multi-valued attribute, you can identify the proportion of various ethnicities in your population and come up with this kind of a pie chart. And now you are trying to identify maybe the 1,000 outlier individuals, and you might want to say that the blue ethnicity is around 45% in the population. So around 450 of those 1,000 individuals should come from the blue ethnicity. So you can set these quotas and gradually fill in these quotas based on the abnormality scores or outlier scores as your algorithm decides. So in the case of a single attribute, you can achieve some equitable representation among the outlier results by using quotas. And this is and the quota-based system is used not in outlier detection, but in certain other scenarios in the affirmative action policy that India employs and has employed over the last 70 years. So this approach, however, does not generalize for multiple sensitive attributes, and that is where we have this work trying to achieve fairness over multiple sensitive attributes. So let's look at some background about neighborhood-based outliers. There are various ways of characterizing outliers, and one paradigm that has gained increasing acceptance in the last 2 decades has been that of neighborhood-based outliers. So here, let us say that we want to identify the outlier score of an object. And in this case, let's take a look at the bottom left blue object. What you would do is you decide on maybe a value of k, and in certain cases it could be maybe 5, let's say, and now you draw a circle which contains which is at the k, which has the radius as the kth nearest neighbor distance. So the fifth nearest neighbor distance, and you draw a circle, and that gives you the local neighborhood space that this object is situated in. And you can draw this and you can identify maybe the density of these the density of the space by using the density of objects in the space in the local neighborhood, right? So in this case, I've used k equal to 3. So I've drawn, I've taken this object right here as the object in question, and taken its third nearest neighbor, which is this one, and drawn a circle with that distance as the radius. So that is what you have here. And if you draw the similar third nearest neighbor and 3 nearest neighbor circles around each of its three nearest neighbors, those are these 3 points, you will get these circles. Okay, and as you can see, these circles are much smaller than the circle that we drew earlier. So what does this mean? This means that the neighborhood of those neighbors is much more dense than the neighborhood of the object that we have in question. The object is in a much sparser neighborhood than that of its neighbor and than that of its neighbors, and that is indicative of this object being an outlier. So let's look at what could be the potential unfairness in outlier detection. And let us say that you have data about individuals, and let us say that you have a gender grouping, and the gender is represented by using colors here. So let's say black is women, and blue is men. And so if we do this kind of a k nearest neighbor analysis, and you're trying to compare the neighborhood of this object along with the neighborhood of its objects, with the neighborhood of them with their neighborhoods, and then what you are achieving here, you are comparing the neighborhood of this black object against the neighborhood of 5 others. So here I'm using k equal to 5, and when you look at these 5 other nearest neighbors, then all of those 4 objects come from the majority category, which in this case is male and blue. So this means that you're contrasting the minority category object with abundant demographic groups, right? So that is what causes unfairness. This could be a source of unfairness in outlier detection while using LOF. So like I mentioned here, our solution is to factor in sensitive group memberships into the outlier scoring process. And we'll see how we do with it. So the one thing that is central to our method is this notion of sensitive attribute groups and ensuring group fairness in LOF scoring. So our method is called fair LOF, and it's a group fair version of LOF. In order to make the LOF computation fair, we adjust the k nearest neighbor distances by making use of sensitive attribute group membership. And we formulate 3 principles, and these 3 principles are put together to form our LOF score, to form the fair LOF scoring method. One is called the neighborhood diversity principle, the other one is called the a priori distribution principle, and the third is called the attribute asymmetry principle. We'll look at each of them separately. So let's look at the neighborhood diversity principle. So here, as you can see, the black object is compared with its neighborhood, which is predominantly blue. Right. So here the neighborhood diversity among the 5 nearest neighbors, 4 of them are from a different demographic group. So you have 4 over 5, and that is what we call as a neighborhood diversity. And you can and what you would do is you take the k nearest neighbor distance, which is the distance to the 5th nearest neighbor, and scale it down by using this neighborhood diversity. So if your k nearest neighbor distance is 10, you take 10 times 1 minus lambda into 0.8. So it will be much less than 10 when you do the scaling. So that is the way we kind of factor in the neighborhood diversity into the k and distance scoring process. And this is because by this black object being compared with this blue objects predominantly, and the blue objects being fundamentally different due to the sensitive attribute grouping, it tends to be the case that the distances, the k nearest neighbor distances, tend to be higher for minority objects, right? Because they are compared with majority object groups, and the majority object groups are generally different from it. So here we are trying to remedy that issue by using this sort of a scaling process. So you discount the k nearest neighbor distances of objects in highly diverse neighborhoods, and you note that the minority objects will get their k nearest neighbor distances discounted more. So the more the k nearest neighbor distance, the more the likelihood, although it's not a direct relation, but the more the likelihood of them being classed as outliers. So let's come to the next principle. So let us say that you have not just 2 groups, but you have maybe 3 groups. Let's say that this is ethnicity, you have 3 ethnicities, and you see from the distribution that while the blue ethnicity is the majority, and the second most frequent ethnicity is red ethnicity, and the least frequent is the black ethnicity. So given the distribution, the black objects are only a very small fraction of the entire population, so their k-n distances would get deeply discounted. We don't want to do that. We want to discount it only appropriately. So we scale the discounting by their a priori distribution. So we'll look at how to do that in terms of a formula, but the details are in the paper. And coming, so we talked about objects and their neighborhoods. We talked about object attribute values and the distribution across those object attribute values. Now let's look at how we deal with multiple attributes. So it's not just one attribute of unfairness. It could be gender as one attribute, and ethnicity could be another attribute, and there could be many attributes as well. So each of the above measures that we looked are computed within groups defined on one attribute. when there are multiple attributes, each attribute suggests a discounting for the k-nearest neighbor distance. And what one could do is to simply add up all these discountings and then discount the k-nearest neighbor distance in one go. But certain attributes might be more responsible for unfairness in outlier detection as compared to certain other attributes. So what we do is we weigh the attributes appropriately, and we weight the discounting coming from each attribute using an attribute level weighting. And the attribute level weighting is determined using the level of skew in the raw LOF results as measured on the attribute. So let us say that you're taking gender and you have 50-50 representation in the population, and it appears that you have, like, let's say 50-50 representation among the outliers in the raw LOF results. So you don't do much discounting. Whereas in another case, let us say that you have ethnicity and you have an 80-20 distribution, and there is a deep skew in the LOF results as well. Then you give a higher value for the discounting that is coming from the ethnicity attribute. So the fair LOF KNN distance computation looks like this. So you look at the original K distance, that is what is shown on the left hand side, and then you weigh by this one minus lambda times, and lambda is a weighting factor. And the first thing is an attribute asymmetry. It depends on the attribute. It is scaling. Maybe the gender has a weight, ethnicity has a weight, etc. And the second one is the a priori distribution. It depends on the attribute value. So here, male has a weight, female has a weight, white has a weight, black has a weight, and so on and so forth. So this weighting is at the level of attribute values, and this weighting is a neighborhood diversity weighting, and that is at the level of individual objects. Right. So you look at decreasing level of generality. This is the most general at the level of each attribute. This is at the level of attribute values, and this is at the level of individual objects. So for evaluation, we look at two kinds of metrics. One is the fair LOF results, and the fair LOF scores should be as close as possible to LOF. We don't want to deviate too much from the raw LOF scores. Whereas in the other case, you look at and that is the quality condition, and in the second one you look at the fairness condition. How much fairer are you making the anomaly, the outlier detection results on as measured on these sensitive attributes? So ideally we would want to achieve a high improvement on fairness, right? And we would want to achieve a high improvement on fairness at very low deterioration to the quality of the results. And this is some deterioration is expected because you don't expect to get fairness for free. You expect to get fairness at some cost, and this cost should be as low as possible. So here I have the results that we achieved through looking at various data sets. So you look at the quality of the outlier results, and there are there is one way of quantifying it, which is using the Jaccard similarity. As you can see, there is a deterioration here. This is the deterioration that fair LOF has as compared to LOF, around 10 to 12% deterioration. Whereas if you look at the LOF scores, the LOF scores are not deteriorating by much. So this is like saying that I don't get the top 10 right, but the top 10 anomalies or the top 10 outliers that I detect already have very high outlier scores even when judged using LOF. So as you can see here it is very little differences. The deterioration is only less than 1%. When you look at the fairness metrics as measured using Euclidean distance and Wasserstein distance, and this is what is used in order to quantify fairness using these proportions over sensitive attribute groups, etc., you can see that there is a big jump in many of these fairness measures. So there are high numbers such as 54, 55, etc., and there are reasonably small numbers as well, but they are very few. Most of them, on an average, you get much higher improvement in fairness as compared to the quality deterioration that you get over the LOF results. So in conclusion, we motivated the case of fairness in outlier detection, and we presented the first work on fair algorithms for outlier detection. We looked at fair LOF as a neighborhood-based outlier mechanism that is oriented towards producing fair results through discounting at 3 levels, through KNN distance discounting at 3 levels, and we showed that we achieve significant improvements on fairness at low to moderate degradations in outlier detection quality. So that brings me to the end of this presentation. If you have any questions, feel free to contact me at deepaksp@acm.org.